Hey guys, we're going to go ahead and start the webinar right now. We had some technical issues earlier with our sound, but we were able to resolve it. So I apologize for that. And because of that, I just need to do the recording. So this is going to be fairly short. This is the evolution chapter that we're on right now. And I'm going to go ahead and do this webinar as if we were doing it live because of the technical issues. But I'm going to go ahead and share my screen right now so that you can follow what I'm doing. Okay, you should see my screen right now. And just to let you know that all of your grading should be caught up sometime today. This is Tuesday. And so anyway, as far as today's chapter is concerned, this is the last chapter. There's not a final exam of any kind. You just need to finish your quiz and your lab report for the evolution chapter. So anyway, it's just like all of the other modules. Make sure to do the reading that's indicated in the learning outcomes. And then the PowerPoint that I'm going to go through right now is already in your module. I just wanted to walk you through it step by step. And even if you read it before, it'll be a good self-test. But if it's new, this will be especially good for a preview. Then make sure to do the lab report. If you have any questions for the class, then you can put it in the Q&A, and either a student can answer it or I can answer it. But of course, if you have specific questions, I don't mind if you message me on Canvas, and that's probably the quickest way to ask individual questions. And then of course you have the quiz here. So let's go ahead and go to the PowerPoint right now. And guys, I apologize for the technical issues, but this is our I told you that those of you who were on that webinar earlier, I left a message in the chat box that I would record this and you'll be good to go. Okay. And so this is just about as good as being there. I realize that you won't be able to ask questions during this webinar because this is just a recording. But if you have specific questions that don't get answered, then please go ahead and message me on Canvas, and I'll answer those as quickly as I can. Okay, let me get a drink here real quick. So this is kind of a fun chapter where we combine, fossil evidence with evolution. So, so we should be done in less than a half an hour, especially where this is just a recording. I'll even keep it shorter than that. So first of all, your chapter talked about Charles Lyell, and it said that Charles Lyell said that the surface of the Earth was altered by natural processes, and that older layers were lifted up by the movement of the Earth's crust. He found that the deeper, older rock layers did not have fossils of modern animals. So that was kind of a clue. And then on the other hand, later on, Charles Darwin built on Lyell's theories, and he said that if the Earth did change, then the organisms would change over time. In his travels all over the Earth, and they're well documented, he collected evidence that supported his hypothesis. Now, your lecture professors are going to talk in detail about what Darwin did, the Voyages of the Beagle. He even wrote a book called, Origin of Species. I was required to read that when I took an evolution class, obviously, but it's pretty well documented. For example, when he went to different islands, he noticed that that finches were slightly different on the different islands, and that their beaks and other features were able to adapt best to their environment. So he postulated that organisms change over time, and that those adaptive changes, those positive adaptive changes, can be passed on to offspring, and that's how those changes occurred. So again, your teachers will talk more about that in detail. Now, the lab manual talks a little bit about radioactive dating and decay. So it's a way that we're able to date not only the Earth and the strata that are in the Earth, but the organisms that are in those stratified layers. So what happens is that in radioactive decay, elements found in rock layers can exist in multiple forms called isotopes. Isotopes are just different weights of atoms, mainly because maybe they have more neutrons than the stable isotope or the stable atom does. So anyway, they can decay into different kinds of elements. So isotopes can be converted into other elements over time, and that's what's called radioactive decay. So for example, uranium-238 can be broken down into lead. Carbon can be broken down into other forms. We often use carbon dating, carbon-14 dating, because it has a relatively short, fast half-life, and it's the primary way that we could date organisms. But as far as the Earth is concerned, and because it's so old, uranium-238 can be used to date different layers in the Earth's crust. So here's the idea with half-life, okay? Half-life is the time it takes for 1/2 of an isotope to decay. So guys, if I were to do this lab live, if I were to do this PowerPoint live, I would ask you these questions. So I just want you, if you need to, you can just pause the video and answer these questions yourself. So right here, it represents the first block here, or sphere, represents the undecayed uranium-235. Now, when it goes through its half-life, it takes a, this just represents that half of the uranium is still there, but the other half is lead, because we said earlier that uranium-235 decays into lead. And so another half-life, you just divide that in half. So how much lead would be available in another half-life over here? So stop the video if you need to, just see if you could answer real quick. How much lead would be available in another half-life, and how much uranium would be there? Okay, so it's 25% uranium and 75% lead. So it's half and half and half all the way down. And your lab manual talks about this. They show it a little bit differently, but it's the same idea. So how much uranium would be available after another half-life? So again, you just cut that 25% in half and increase the lead. So 12.5% uranium is available, but 87.5% of all of that would be lead. So you can see that over time, you end up getting more uranium 235 and more of the lead. So what is understood through lots of experimentation, which we don't have very much time to go through right now, but what they've determined is that uranium-235 has a half-life of about 4.5 billion years. So what would be the how much time would go by before we have only 25% uranium left, but 75% lead? So how much time would go by? So that goes back to 2.25 billion years from now. 2.5 billion years ago would have given us 75% lead and 25% uranium. And then this is from the beginning of Earth time, and then over here it's 1.125 billion years would be 87.5% lead and 12.5% uranium. So over time, we get more and more lead available the younger the strata are, because it's had more time to decay, right? So 87.5% is now lead. So that's basically how it works. Every half-life is a certain percentage toward the new element. So you can do the same thing with carbon-14 dating too. Now, another thing that I wanted to show you is how you can date stuff depending on how much of the sample is available. So this is a graph. This comes right out of your lab manual, but I just wanted to go through it because there was confusion about it when I've taught this lab in the past. In fact, there was confusion on this slide too, and that's why I wanted to go through it. So this is right out of your lab manual. So the question is what would be the half-life of this sample? Now, I mean, you have a graph over here, but you have to determine the half-life by looking at the number of grams of the original isotope in the sample. So that's on the y-axis right here. So it starts out with 250 grams. So when you analyze that, and you only have half the number of grams of the original isotope in the sample, all you have to do is take a straight line and go right to this half-life scale, and then go down. And so, what would be the millions of years, the half-life of this particular sample? Let me give you a few seconds to decide that, and then see if you can figure it out on your own. So the half of the number of grams, 250, would be 125 about, right? So you go over from left to right where it meets the line. This is your standard line, okay? So then you go straight down, and it looks like it's about 80 grams. I mean, I've already penciled it in here. I'm sorry, not 80 grams, but 80 million years. So that's what it is right there. Now, what if you only had, let's say, 30 grams of the original isotope? Only 30 grams of the original isotope right here on the y-axis. And you can see I drew it in here already. So this is about 30 grams. It might not be perfect. You should have used a ruler on this, but so you carry it over, and it's going to be around 230, maybe 225, something like that, million years. So a rock sample containing 30 grams of the original isotopes represents how many years again? So about 225 or 230, 240 maybe. I probably stretch it a little bit because my line isn't perfect. If you were able to do this on Excel, then you would have an exact number. So this is about, I mean, I wouldn't mark you wrong if you were plus or minus about 5% here. So anyway, that's how we do that. That's how we, when a geologist digs underneath and they dig through the strata and they analyze the isotopes of the different strata, they're able to determine approximately how many millions of years back that strata is. And if we're talking about carbon-14, this is more relevant to carbon-14 dating, because that's what's important to us as far as living things are concerned, or I mean, living organisms, because living organisms just existed in the last, 5% of the history of the earth, give or take a little. Okay. Now I wanted to show you, talk a little bit about fossils for a minute. And if we were in the lab itself, we actually give you some fossil examples, and these aren't perfect fossils. I mean, keep in mind when an archaeologist digs for fossils, there's all kinds of dirt mixed up with it that's hardened up, and they have to carefully remove the sediment and extract the fossils. And so in the lab, we actually give you something that looks kind of like a rock that has just an imprint of a fossil in it, and they're usually not perfect. And so what we do is we have you look at those rock samples and those fossils to help you go through an experiment where you can just hypothesize what the changes may have happened. And it's kind of hard for me to explain it right now. The best thing to do is to go to your lab manual and just kind of read through the procedure, what we actually do in the lab. And all you can do in this, because we're in this remote activity and we can't touch the fossils, just do your best in answering the questions the best you can. But what I want to mention as far as those fossils are concerned is we would indicate, which layer of sediment those rocks came from. So within each sedimentary layer are fossil remains from organisms that existed only during a limited period of geological time, and those are called index fossils. So in the lab, we would give you index fossils, and then you would answer questions accordingly. But anyway, what I want to mention is that index fossils are representative of only one time period, and so they can be used as indicators of the age of the rock strata in which they're found. Because they're only existing for a real short, limited period of time. So that's why they can be used as indicators of the age of the rock strata that they're in. Rock profiles, I'm going to show you a rock profile here in a second, but they help us to determine different things. Rock profiles show vertical sections through two different rock formations, and these are actually diagrams, and here's one right here. This is also from your lab manual. So if you visualize this, the one on the left would be the original rock strata, and we have different layers of rock that are labeled different things. And I know this isn't alphabetical, but just kind of go with me here for a minute. The ones on the right, this rock strata on the right, these would represent the change that's occurred in those rocks over time. And remember, as each layer is put down on the earth, whether it's sandy sediment, maybe it was originally an ocean sediment or whatever had created it. For example, here in Utah, we had, it's well known that there was Bonneville Lake, and Bonneville Lake covered all of Utah. And it was massive, and the Great Salt Lake is just a remnant of it. And so we have sedimentary rocks that are throughout Utah, and over time, each layer, after it was built up, and after earth movement and earthquakes, etc., there's also a certain amount of erosion, and the erosion tends to be faster than the uplift sometimes. Not always, depending on how hard the rocks are. But what's left over the years on the right-hand side is the eroded rocks from the different layers. And some of those layers may have gone away completely. Some of them may have just been smaller than they originally were. So anyway, if you were to compare the rock layers on the right with the ones on the left, you could kind of visualize, if you took this layer on the right and moved it up, you could line up like this layer F with the other layer F. And then if you go down a little bit further, these other layers in letter A over here, the ones on the left, these have eroded away until you got down to letter Z here. And then the next one, O, would have worn away, and then you have B left. Okay, you see that where I've drawn the lines? And then we have P left over. That means that J eroded away, and so on and so forth. So that's how we can compare the older layers with the newer layers. And it looks like on this example here, everything below P would have eroded away. In other words, U, L, and G would have eroded away on the left-hand side. Well, no, that's incorrect. Sorry, I said that wrong. No, U, L, and G is still there. It's just that they're not showing on the left-hand side. So anyway, let's answer a few questions here. This will help you out with the lab manual a little bit. So profile B was weathered away. It has weathered away strata at different times. Profile A represents the original unweathered strata. Okay, so let me ask you this question right now. Which letter represents the fossil layer that has the youngest in both profiles? The youngest in both profiles. Okay, so if you were to compare the two, what would be the youngest in the profiles? So if you moved up letter B up to where it matched up, F with F, layer F with layer F, what would be the youngest layer that's still present? So obviously it would be letter S. So letter S is the youngest profile because it hasn't had a chance to weather away yet, or not as much. Okay, which letter represents the fossil layer that is the oldest in both profiles? So comparing both of them, you're lining up like P with P here and move letter B down. Which one would represent the oldest strata? Well, obviously it's the one that's deepest down, right? So the one deepest down would be G on the right-hand side because P and P line up here on the left and right-hand side, and U, L, and G go down. So U, L, and G are the oldest, but G is the oldest. And S is the newest because it's on the top layer, the one that was laid down first that still exists, and it hasn't weathered away yet. So letter G would be the oldest. Okay, now, with letter G being the oldest and S to be the newest, now let's compare what matches, okay? And I've already alluded to it. You can see it in my lines here. So which rock layers in profile A have matching layers in profile B? Okay, which ones would they be? Okay, so you can see F and F match up, Z and Z match up, B and B match up, and P and P match up. So they have matching layers. So what that could tell you is that those layers are taking longer to erode, and maybe they consist of originally either thicker layers or more likely harder layers. But that's how they analyze these strata. And you know, depending on whatever organisms could be there, those index organisms can be an indication of how old they could be. Okay, so F, Z, B, and P are the layers that match up. Okay, now here's another thing that we have. This is also out of your lab manual. These are examples of life that are in past geological periods. And you can see the different geological periods right here, different living organisms, and the millions of years that these different layers have been dated. And so if you were to examine these layers, you would find the organisms on the right, like Ordovician has marine life, Silurian has corals, etc., and all the way down to dinosaurs, which were 80 million years ago in the Cretaceous period, dinosaurs, plants, and that produce seeds, etc. So my question is which geological period do you think would be represented by the thickest layer in the rock strata? The thickest layer in the rock strata. Now remember, the thickest, that's assuming, we're assuming that all of the layers have the same types of rock basically. And I realize that's not always the case, and geologists are able to factor that in. But so we're just assuming that all of the layers have the same, basically the same kinds of rock. So which geological period would represent the thickest layer? So the thickest layer. So if they all eroded in the same rates, the thickest layer would be the one on top, right? The most recent layer. So which one of these would be the most recent layer? It would be the one that's 28 million years ago, right? Okay, because it hasn't had enough time to erode, as much time to erode, that is. So that's the Silurian, because it had the least amount of time to erode. Now, let's ask it the other way. Which one would be the thinnest? Okay, which would probably have the thinnest layer? Okay, give you a second to think about that. Look at the numbers. Okay, so the thinnest layer is the one that had the most time to erode, right? The one that went through the most erosion would have been the one that had the most time to erode, which is 80 million years. So that would have been our Cretaceous period. So by looking at their thicknesses and the layers, we're able to determine not only age, but we're also able to estimate which organisms we can predict might be in those layers. Okay, so guys, that's basically all I wanted to go through today. This lab today is actually pretty much self-directed. Um, so make sure that you go through all three activities in this evolution chapter and answer the questions in this evolution chapter. Now, as far as activities 2 and 3 are concerned, I haven't talked very much about the fossils and the other activities in the evolution portion of this lab, because they really are really self-directed, and I think you'll do just fine by going through those just with your manual itself. So be sure to complete all the questions to prepare for the post lab and the quiz. Also complete the self-test that's at the end of the chapter. Now, guys, I realize that I'm not going to be quizzing on, I'm not going to be checking to see if you did those questions in your manual, and also the self-test, but it really will pay off in the long run on the post lab and the quiz if you take the time to go through those questions, answer them, and do the self-test. Okay, and there's no reason why you can't get a high score, 100% on everything if you prepare well with those questions that are in the manual, and then go to the post lab, and then go to, make sure to go over this PowerPoint again. The PowerPoint's in the module, and go through any part of this this recording that you need to. Anyway, good luck. Make sure to turn everything in by their due date. Talk to you later. Bye.